Good morning, my friends. Sorry I can't be there today. I have some things I have going on today I have to take care of. But I did want to move us forward. So I put together a little video here for us. Move this down a little bit. About balanced and unbalanced forces. So you can take your lab notebooks out, please. Turn to the next open page and make an entry for today for balanced and unbalanced forces. I'll give you a chance to get caught up there. Now, one of the really great things about doing this as a video is that if you start falling behind, you can simply ask the guest teacher to pause the video, and I will warn you before I move on from one set of slides to another slide, so that if we do need to pause, you can. All right. Great, let's get going. Today we're going to be talking about some conclusions from the Getting Pushy and Cart Mayhem lab. Those are the last two labs we've been working on. And then we're going to talk explicitly about the effects of balanced and unbalanced forces on the motion of an object. All right, let's get started. So Getting Pushy and Cart Mayhem. Those are the first two labs, so Roman numeral 1, Getting Pushy and Cart Mayhem. One of the conclusions that we got from Getting Pushy lab especially is that to stay at a constant speed, we have to pull forward as hard as friction pulls us back. So let's do a little quick force diagram here. I've got my cart, and I've got my little person sitting on my cart. I don't know why their neck goes up into their head either. That's kind of weird. And I'm going to draw the ground here as well. And my ground's a little wavier than what it should be. So my forces that I'm talking about here, let's put the forces in red. We're going to have force here of the earth pulling down. And of course, to keep you from falling, the ground is pushing up. And these are things we've done before. Now the next thing that's going on is that this cart here is being pulled forward by someone, but it's also being resisted by something, and that something, of course, is friction. So we'll push backwards in this way, and we'll say that's the force of friction, which we should understand as being the force of the ground pushing backwards. This is not an object. Every other force we label as an object here. This one I want to label as friction so we don't lose track of the idea of what it is. So really it's the force of friction with the ground. And it's the ground pushing back. And then there's a forward force of a puller. Force of, let's say, you pulling forward. And what we found is at constant speed, what we need to do is the force of you has to equal the force of friction. And when you manage to do that, you end up going at constant speed. So let's say that the friction was 15 newtons. Well, of course, that means then you have to pull with 15 newtons to go at a constant speed. So that was our first conclusion from that lab. Our second conclusion was, hey, in order to speed up, we actually had to pull a little harder than friction. So we had to give it an extra little tug. But in order to stay at that faster speed, we still pulled forward with the same friction as before, which is kind of surprising because we might think that going faster requires more force, but really, it doesn't. So I'm going to click back over here to black. And let's draw another force diagram. Hey, I got a better road. And I've got my person there, ready to rock and roll. And here I still have, I still have force of the earth. And the force of the ground. And these should be equal. And then even with fast. At a fast speed, the wheels and the ground are still the same. They give you the same friction. So the friction backwards is the same friction. So the forward U pull is the same forward U. So forward, or your force, the force of U, which I'm just now seeing this as probably not too appropriate, so you'll have to get over that. The force that you're pulling with, we'll keep saying the word force instead of the letter F, is still equal to 15 newtons. I'll have to reshoot this for next year. So the force that you're pulling with is still equal to 15 newtons, just like it was before, and that's because the force of friction is still the same. If this backwards force of friction jumped up to like 30 newtons, then the forward force that you're pulling with would jump up to 30 newtons as well. Awesome. So I'm getting ready to move on. So if you need more time on this slide to maybe finish writing something down, then you gotta let the guest teacher know so they can pause the video now. All right, so Roman numeral 2 here is the effects of balanced and unbalanced forces. Balanced forces are the case that we just talked about. It's when the forward force and the backwards force and the up force and the down force, all of those match each other. So the forward will cancel the backward, the up will cancel the down, and it's as if there are no forces acting on the object. So when the forces in opposite direction are equal to one another, we call that balanced forces right here. Okay. Like we just said, the forces cancel out, so it's as if nothing is pushing or pulling on the object. So when we pulled forward with the same force as friction, it's like we got rid of the friction. And when there's no friction, objects that are at rest stay at rest, objects in motion stay in motion. Let's do that part next. So when forces are balanced, there are two possibilities. Possibility number one, objects at rest stay at rest, objects in motion stay in motion, and remember, it's a special thing. They travel in a straight line, constant speed. So there's no speeding up or slowing down, and there's no turning. So in essence, all of this means when forces are balanced, there is no acceleration. That is the key. These two things say no acceleration. You need to know it both ways. So you need to know that it's no acceleration, and that means if they're at rest, they stay at rest. And if they're in motion, they stay in motion, straight line, constant speed. All right, so I'm getting ready to move on to the next slide. If the guest teacher can just pause the video here and make sure everybody's caught up before we move on, that'd be fantastic. So unbalanced forces, if balanced forces are when everything cancels out, unbalanced forces must be when they don't cancel out. So there's some leftover force after you do all the canceling, and it points in a direction. Now this leftover force is an important concept in physics, and we gave it a name of its own, which is called net force. So the net force is the leftover force that you pull. So for example, if you have, let's say that there's a box sitting on the floor, right? And there's a 10 Newton force of friction backwards, and you're pulling with 15 newtons forward, and that's the force of a pull. I won't use you again. So what you do here is you take this 10 newtons backwards and 15 forward, and you ask yourself, well, are these forces working together, or are they going to work together and add to each other, or are they working against each other and are going to subtract from each other? And of course here they're working against. So we take 15 newtons minus 10 newtons, and we end up with a net force of 5 newtons to the right. And this is what we call F sub net. Okay, net force. And we'll deal more with that later. So just like when forces are balanced, there were some possible motions. Same thing when they're unbalanced. So here the key is that either when the forces are unbalanced, they're going to either speed up, slow down, or change direction. There are 3 possibilities. And of course, all of these means that it is accelerating. So balanced forces means no acceleration. Unbalanced forces means there is accelerating. You're making them accelerate. All right, so today for practice, you're going to get to work backwards on this. So you're going to start by evaluating whether an object is speeding up, slowing down, or changing direction, turning. And then from that, you're going to determine whether the forces are balanced or unbalanced, and whether it's accelerating or not accelerating. So you're going to kind of work backwards from from experience back to these kind of concepts. All right, best of luck. If you need some more time with any of this, you can actually just jump on YouTube and search for Joshua Haza, and a series of videos will pop up, but one of them will be this one. Have a great day, my friends, and I will see you tomorrow bright and early. Enjoy your weekend. I don't want to forget to say that. Have a nice weekend.